homework 7 would be published soon. Do this coming Thursday, so July the 15th. Also the day that we have an exam, so it's important that you work on homework 7 before the exam. All right. Let's see. Any questions from the homework? I know that some of you asked a few questions already. Any other questions?
Yeah, I have one.
Go ahead.
It's the integral from 0 to 13 of 1 over the cubed root of 13 minus x.
This one?
Yep.
I believe this is from the 6a part. It's an improper integral.
Correct, yeah.
To know that it's improper integral, you have two ways, right? One is that you have an infinity in that interval that you're integrating over. The other one is that you have an infinite discontinuity. Basically, you have a vertical asymptote somewhere. But just looking at the denominator, we have cube root of 13 minus x. We know immediately that the x cannot be 13. If you put 13 there, you get 0 in the denominator. So we know that x equals 13 is a discontinuity. For x less than 13, like any number between 0 and the 13, if you put it in there, you know that the denominator is always positive, right? 13 minus a number less than itself, it's positive. I'm just going to quickly sketch what the graph look like. So 0 is here, 13 is there. We're integrating in this interval, but 13 is a discontinuity. And the value of the function before 13, that's going to be positive. So I'm just going to assume, I don't know what it looks like, but I'm going to assume that the graph looks like this. You have decimals, you can plot it. And we are looking for this area. 0 is not a discontinuity, but 13 is. So be careful, just keep that in mind. That means that the first step to rewrite this integral, we're going to write as using the limit definition. So that'll be limit t goes to a number. Integral 13 is a discontinuity, so we're going to replace it with t. So 0 to t, 1 over cube root 13 minus x dx. And then the limit of t here, it always goes to that discontinuity, right? It's going to relate it to 13, but is it left or right side of 13? That's what you need to find out. Well, I always look at the area I'm integrating over, because the area is on the left side of 13. So the t value will approach 13 from the left. So t goes to 13 minus. And then let's just focus on this part. Rewrite the function using x. Well, there's a couple of things you can do. Depends. You can use the u substitution, or you can rewrite it using a negative exponent. You can let u equals 13 minus x. So du equals minus dx. Dx equals minus du. Substitute into the integral. I'm just going to write limit integral, but remember that there's a few parts that I'm not writing it out. So that's 1 over cube root of u. Dx is negative du. So du, I'm going to put a negative all the way in front. It doesn't really matter where you put the negative. So, okay. So that's the first step. So that was a question. So if it was from 0 to 12, Correct. So Sam had a question. So if it's if we're integrating the function from 0 to 12 of 1 over cube root of 13 minus x dx, right? So that will be just a normal definite integral because you don't have any discontinuity in that interval from 0 to 12. Good. So let me continue here. So the next step, rewrite the function using exponent. So that's a negative limit integral u to the negative 1/3 du, and then we can find the antiderivative. So that's a negative limit. So add 1 u to the 2/3, divide by the new exponent, so 1 over 2 over 3. And then we're going to evaluate this antiderivative from, what was it, 0 to t that I did not write out in all previous steps. But those are not u values, those are x values, right? Keep that in mind. So that's a negative limit. So 1 over 2 over 3, so that's a 3 over 2. U is 13 minus x to the power of 2 over 3. You can write 2 over 3 as in the exponent as 13 minus x squared and then cube root, if that's easier. All right, this is a square of 13 minus x. And evaluate this from 0 to t. Next step is to plug in those two boundary values, t and 0. So the negative, we're taking the limit. If we plug in t, now I'm going to bring out the 3/2, negative 3/2, because that's just a constant. So plug in t, so that's a cube root of 13 minus t squared, minus plug in 0, so that's a cube root of 13 minus 0 squared, so that's 13 squared. And the constant stays outside. So now we just take the limit of each term. So limit t goes to 13 negative of cube root of 13 minus t squared. And then minus the limit t goes to 13 negative cube root of 13 squared. And because this is a constant, so when we take the limit, it's still going to be a constant, right? So that's a minus cube root of 13 squared, that's a constant. But this term on the left, if we take a number that's slightly less than 13, we put it in there for t. So let's just say, you know, if you look back the x-axis, the number less than 13 is going to be like 12 point some number close to 9, right? 12.99 repeating. So if you put a number there, 13 minus t will be really, really small, right? The difference between 13 and then the number to the left of it is very small. So this part basically goes to 0 if you square that and then take cube root. So this part basically approaching 0. And then you just end up with negative 3/2 times negative. So 0 minus, so that's a negative cube root 13 squared. And then this is the, you can simplify it a bit more. Just a negative times a negative. This is the finite number. Therefore, you can conclude whether the integral is divergent or convergent.
Sorry, how did you know it was to the left of 13 again? Like to the next?
I use the area that I'm integrating over, or you can just think about the interval, right? So we know that we're integrating from 0 to 13. 13 is a discontinuity, but we're integrating in this part. So when we pick the t, we want the t to approach that discontinuity. So So t will be approaching 13, but which part is the t approaching 13? Well, t has to be somewhere in the part that we're integrating over. So t has to be somewhere in that range, in that interval from 0 to 13. The only way that t could approach 13 is from the left side of 13. So that's why I picked the 13 minus here.
Okay. I just have one last question on this. If you were to swap the 0 and the 13, like the 0 being on the top and the 13 on the bottom, would it be to the right then, or would it still be to the left?
It's still the left. It's all, so the value that the t approaching to is always depends on the interval and the relationship of the interval to that discontinuity. Because in this case, whether you have 0 to 13 or 13 to 0, that interval 0 to 13 is always to the left of the number 13.
Okay, thank you.
Right, but let's just say you have another question that you have a 0 to 13. Let's just say you have 1 over x dx. Right. In this case, the 0 is the discontinuity. The interval that we're integrating has a 0 here, 13 here. This is the interval that we're integrating over. That's to the right side of 0. So the t has to be between them. So t is up. So when you write down the limit, so limit t approaching the discontinuity 0, it has to approach 0 from the right side because the interval we're looking at is to the right side of 0.
So it's basically whatever way it's approaching the discontinuity?
Exactly.
Okay, that makes a lot more sense. Thank you.
Good. I'm glad you asked. Okay, good questions. Any other quick questions before we move on? All right. If you don't have any questions, I'm going to move on to today's topic. But before we do that, I want to kind of remind you what we did last time. So last time we talked about series. So last lecture, we talked about series. And then we talked about series being convergent, the definition. So definition of series convergent says, if the sequence of partial sums of a series, so a series is S equals A1 plus A2 and so on, right? So that we can use sigma notation of AN going from 1 to infinity. Well, before I do that, maybe I should quickly write down what partial sum is. So partials, so S1, S2, or Sn. Let me use I here. I going from 1 to infinity. Sn will be A1 plus A2 and all the way adding to An being the last term. So that just going from I going from 1 to n of AI. So that's a partial sum. So if the sequence of partial sums we write as Sn sequence, if that sequence has a limit that's a finite value, then make sure I don't get anything. Then the series that we're looking for I going from 1 to infinity AI is convergent. So you can figure out whether a series is convergent by making a list of partial sums and then take the and then look at the sequence of partial sums and try to find the limit from there. Right, so that's the definition. We also talk about a divergence test. So divergence test, which says, so suppose that we consider a series. So consider a series I going from 1 to infinity of AI. I forgot I use I or N, but it doesn't matter. Probably use N, but it doesn't matter. So N going from 1 to infinity. Consider series, and the AN, the individual elements, if we put it together, they form a sequence. So AN are elements of sequence AN, right? So if we add those together, we get a series. But if we look at them individually, they are elements of a sequence. The divergence test says if limit AN, so limit of the elements in the sequence as n goes to infinity, is not equal to 0 or does not exist, or the limit doesn't exist, means it's infinity, or you just cannot find it. Then if that's the case, if it's not 0, or if it doesn't exist, then the series n equals 1 to infinity AN is divergent. This is only useful when we try to show some series is divergent. It's not useful if we try to show some series is convergent. So for now, if we want to show something is convergent, we have to use a definition. So that's the divergence test. Just a quick review there. And today, we're going to look at a few other things, but let me give you an example first. For example, so let me note. So cannot, let me write this. If limit AN n goes to infinity equals 0, cannot conclude whether it's convergent or not, or divergent. Conclude if the series is convergent or divergent. We cannot decide if that's the case. Here's the example. If I give you a series, let's say n going from 1, doesn't matter, I'm going to pick n equals 2 to infinity, 1 over n natural log of n. Right? Is this convergent or divergent? Well, you probably think, let's try to use the divergence test to see if it's divergent, right? So let me practice to use the divergence test. So try divergence test, which we're just going to pick the AN from there. So that's the AN part, right? Each element is in that form. If we put 2 in there or put 3 in there, they're all in that form. So we want to know if the limit n goes to infinity of AN, which is the limit n goes to infinity of 1 over n natural log of n. Is this going to be 0, or is it finite number, or is it infinity? What do you think? Anyone know what's the limit of this one? If n goes to infinity, it's 0. Excellent. Because this one you don't need L'Hopital's rule, right? Good job. Because if we just kind of like imagine we can take infinity, put it into the denominator. So that will be just 1 over infinity times natural log of infinity. If you remember the graph, the natural log function, as the input goes to infinity, the natural log of the bat of infinity approaching infinity. So basically this end up to be 1 over infinity times infinity, infinity. So that goes to 0. So you're all right there. Well, that's the thing though. If we try to use a divergence test, the limit of an is actually equal to 0. So that tells us that, so this part that I wrote in red, so this tells us, so since limit n goes to infinity equals 0, we cannot conclude whether it's divergent or convergent using the divergence test. So if you want to know if it's convergent or divergent, you have to go back to the definition, try to write down the partial sums, like find S1, S2, S3, and then try to look at the elements in the sequence, see if you can find the convergence or divergence from there. But sometimes that's a lot of work, it's difficult. So people develop other tests that we can use to find the convergence or divergence. So that's the first thing I'm going to talk about today. It's called integral test. So I just want to point out that all those tests, they don't work. So you cannot just have one that works for all series, right? So some of them work for a certain type of functions. Some of them work for another type of functions. There's no like a one formula for everything. It's not that simple. So you kind of have to practice, and then you will get better at this. Just a lot of tools in the toolbox now. You have to kind of figure out when to use which. It's kind of like an integration and a differentiation, right? You got a lot of different techniques. After you practice, you will know when to use which rule. So here, the first one is called the integral test. Again, this is to test if, so to find if a series, I'm just going to use sigma an, means a series, is convergent or divergent. That's what the integral test is for. So let me write it down. Let me draw a diagram, and then I'm going to write down what the test says. So the diagram is that if we consider a function, f of x looks like this. Let's see, this is a 1, 2, 3, 4, 5, 6. And I'm going to just go up to the function and draw a rectangle. We have seen this before in integration. So that continues, right? I'm going to shape those rectangles. So what happened is that if we sum up all those rectangles, we basically end up with a good estimation for the, well, not really good, we end up with an estimation for the area beneath the function. So we can just say integrating from 1 to infinity of f of x dx, that's the area beneath the curve. That's almost, well, that we can using an approximation, which is, let's call this f1 times 1, just f1 plus f2 times 1. The width of the rectangle is 1 for all those rectangles. f3, and so on, right? And if f1 is the first element in the sequence, f2 is a second number in a sequence, f3 is another number in a sequence. So basically we take all those y values, we make a list of them as a sequence. Then we can just say the integral is approximated by a1 plus a2 plus a3, and so on, with the sequence being, so with the sequence an being f of n, the y value. So the y value at those integers. And then this is just a series, which is just series an, and going from 1 to infinity. So that's graphically, that's a relationship between a series and the integral, which give you the area of area underneath the curve, and the series give you the sum of all those rectangles with width as 1. Right, so let me just rewrite. So 1 to infinity f of x dx can be approximated by the series n going from 1 to infinity of an, where an is basically f of n, the y value at each integer. Right. So that's the part that we will use in this theory, in this integral test. So now let me write down the integral test definition, then we will use examples to show how it works. So integral test. Before I do that, any questions about the diagram I'm drawing, and also the trying to make the connection between the integral, which give you the area, and then the series there. So this part, the diagram, and this, just try to draw the connection between the series and the integral. So the integral test says, suppose f of x is a continuous positive decreasing function on the interval from some k to infinity, and f of n for each integer n in that interval, f of n is equal to an. So the y value is just equal to the value of the element in the sequence. Basically, that's what that says. Then, if the first one, if the integral k to infinity f of x dx is convergent, then the series n going from k to infinity of an is convergent. So that's the first part of the integral test. What this says is that, so if we consider the area beneath the curve, this area beneath the curve, if we consider that area, if the area is finite, so if we, the total area beneath the curve, if that's finite, then the series is finite, means that if you add up all those rectangle areas, you also get a finite total area. That's what that says. So if area beneath area under the function f of x is finite, then the series is convergent. Means the sum is also the series, or the sum of series is finite. And just want to point out one note is that the an here is basically f of x. So if we replace the n with x, we get the f of x. So that's the first part. The second part of the integral test says, if the integral k to infinity f of x dx is divergent, then the series and going from k to infinity, an is divergent. So if the total area underneath the function, the yellow shade, the area shaded in yellow, if the total area goes to infinity, then the sum of those rectangle areas also goes to infinity. That's just using integral and a series, the connection between them to determine if a series is convergent or divergent. Any questions about this? It's probably confusing to you now, but let me know if you have any questions. I jump into the example. So the example, I'm going to use the first example that we did earlier. So we had sigma n equals 2 to infinity, 1 over n natural log of n. We had this. Is this convergent or divergent? Earlier, we said we cannot decide using the divergence test, right? And we did not try to use the partial sums because it could be a lot of work. If you're interested, you can try to do it on your own later. Well, let's try to apply the integral test. So apply integral test. This part is an, right? The formula for each element in that series. So this is an. And the first thing I'm going to do is I'm going to write down the function. So f of x, f of n is an. So f of x is just, so note f of n equals an, therefore f of x, it just a with the an with n being replaced with x. So that is 1 over x natural log of x. Right? And then we're just going to try to find the integral with f of x. So integrating n going from 2 to infinity. So x will go from 2 to infinity. F of x, 1 over x natural log of x dx. And we want to know if this is convergent or divergent, because the convergence of this integral will decide the convergence of the series. So let's try to find this integral. So again, by just looking at it, this is a in this interval from 2 to infinity, we know that when you have an infinity there, this is the improper integral. So we're going to have to use the definition with the limits. So limit t goes, this is the type 1, right? T goes to infinity from integrating from 2 to t, 1 over x natural log of x dx. From here, I'm going to try to use a u substitution because I noticed that I have a 1 over x there, which seemed to be the derivative of natural log of x. So I'm going to try to use the u substitution. So I'm going to let u equals natural log of x. So du equals 1 over x dx, or you can write as dx equals x du. Yeah. So now let's put it in there. I'm going to just not write down everything, just limit integral. So I got 1 over x, and then natural log of x is u in the denominator. So 1 over u, you can just write as 1 over x u together. Dx, which is x du. And it's nice that the x cancels, becomes limit integral 1 over u du. And then that becomes the antiderivative would be just natural log of absolute value of u. And we evaluate this between x equals 2 and x equals t. All right, stop me if you have any questions. So that's plug in the u. So that's a limit. Natural log of u. U is also natural log. It's absolute value u, but because we're looking at x is from 2 to infinity, so when we put in, when we calculate natural log of x, that's always positive. So u is always positive when x is from 2 to infinity. So I can just drop the absolute value sign, just natural log of x, evaluate it from t to 2. And then the next step is just plug in those two boundary values. So I get natural log of t minus natural log of 2. I immediately know that's just going to be a number, right? It doesn't matter what it is now, just a number. And the t goes to infinity. So let's look at this. If t goes to infinity, when we take the limit of the first term, so limit t goes to infinity of natural log of t minus limit natural log of 2, that's just itself, constant. As t goes to infinity, this part will go to infinity, right? Natural log of infinity is approaching infinity. And then natural log of infinity, again, that goes to infinity. So the first term is just going to be infinity. The second term is a constant. And that's always going to approach infinity. So that's this infinity at the end is the limit of the integral of this integral that we try to find. Right. So this part of work is something we have done before when we talk about improper integrals. Right. So what does that tell us? If you remember that from a few lectures ago, if we end up finding the limit of an improper integral going to infinity, we cannot make a conclusion, right? Because that's the case, the limit is not a finite number. We cannot conclude that it converges. That's what I meant earlier. So therefore, this integral diverges, or is divergent, because of the limit is not a finite number. Well, if the integral, the improper integral, is divergent, what does it say about the series that we want to find at the beginning? Well, according to the integral test, if the integral is divergent, the series is also divergent, right? The second part. Therefore, the series 1 over n natural log of n is divergent. That's how the integral test works. You take the an, you write down the f of x, then you take the integral of f of x to see if it's convergent or divergent, and then sort of going back to the series, try to make a conclusion from there. Any questions on this? Now, I want to point out that a few things I didn't mention. So in the integral test, the condition is that f of x has to be continuous, has to be positive, and a decreasing in the interval that you're considering. Here, I did not talk about them, but if you look at the function an or f of x, you got 1 over x, natural log of x. This function for x is from 2 to infinity, the denominator is always positive, right? The numerator is positive, so the numerator is always positive because it's a 1. The denominator is x, natural log of x, both are positive, so the function is always positive. Is it continuous? It is continuous because we don't have a discontinuity. Is it decreasing? It is decreasing because the denominator, as x increases, the denominator increases, so overall value decreases. So if you're not sure, you can always use Desmos to plot this function to get a quick visual. But by just kind of quickly looking at the function, we know that it's continuous, positive, and the decreasing on the interval 2 to infinity. So that's sort of the condition.
Can you explain what you did after you found infinity?
At the very end, after I found the limit is infinity.
Yes.
So the limit I found, that's the value for the integral, the improper integral, right? So at the end, I found infinity. That tells that my improper integral is going to approach infinity. So it's a divergent integral. So that integral that I'm looking for is divergent. And because the integral is divergent, then the series is divergent. That's what this second part of that integral test says. So if the integral is divergent, then the series is divergent. So that's what I did. After I found the limit of the integral to be infinity, I concluded that the integral is divergent, therefore the series is divergent. And here we don't need to even find the sum, right? Because if the series is divergent, it's either going to go to infinity or positive infinity. In this case, because of the integral is approaching infinity, therefore the series is approaching infinity. But that's not important because infinity doesn't really mean anything at this point other than just a big number. So we can just, all we want to know if the series is divergent or convergent at this point. The second example, I have a series n going from 0 to infinity of n e to the minus n squared. And I want to know if this is convergent or divergent. You can try to use a divergence test to show it's divergent. Maybe you couldn't make a conclusion if you try to apply it. So here, I'm going to try to use the integral test. By looking at this part, this is what an is, right? So I'm going to write down f of x that I'm going to use in the integral. So f of x is just x e to the minus x squared. And the interval that we're looking at is from 0 to infinity. That's the value for n. So I want to know if the series is convergent. I'm going to consider this integral first, which is from 0 to infinity, f of x, which is x e to the minus x squared, dx. I want to know if this is convergent or divergent. Well, to do that, again, this is this is the type 1 improper integral. So we can write it using the limit definition, just like the previous example. T going to infinity of 0 tx e to the negative x squared dx. Again, at this example, if I want to integrate, what should I do if I want to integrate this? Should I use integration by parts, or should I try something else? Any suggestions? Integration by parts? That's a tricky question. It's actually, we can use something easier, right? Integration by parts is a little bit more challenging because you get a negative x squared in the exponent of e. So because we have this part in the e in the exponential form, so I probably wouldn't try to use the integration by parts because it might not be easy. I might work. You know what? Let me take it back. It might work, but I think it should work. But I'm not going to use that. I'm going to use u substitution, which is easier. So let u equals negative x squared du equals negative 2x dx. And the dx will become 1 over negative 2x du. So use substitution. So that becomes limit integral x e to the negative, no, just e to the u times 1 over negative 2x dx du. The x will cancel the negative 1 over negative 2. I'm going to bring it in front of the limit. So that's a negative 1/2 limit integral e to the u du because of the x canceled. So that's a negative 1/2 limit integral u du. That's just, sorry, e to the u. So that's e to the u, and evaluate it from 0 to t. Those are x values. So I'm going to replace the u. So limit e to the u, which is e to the negative x squared, evaluated from 0 to t. So now I can find plug in those boundary values. So that's a negative 1/2 limit. And plug in t, so e to the negative t squared. And then we have minus e to the negative 0 squared, so e to the 0, which is 1. And then now the 1 is always a 1 when we take the limit as t goes to infinity. What about the first term? If you don't see it immediately, you can rewrite it as 1 over e to the t squared as t goes to infinity. That might be easier to see. And then minus 1, just minus 1. Next step is take the limit as t goes to infinity, t squared also going to infinity, right? So this part becomes infinity. And the e to the infinity is infinity. 1 over infinity is 0. So basically that tells us this first term, when we take the limit, it's going to approaching 0. And then we just end up with negative 1/2 times negative 1, which is 1/2. This tells us that the limit of the integral is 1/2 is finite. So since the integral that I'm trying to find using the limit definition, we get 1/2. So it's a finite number. Therefore, the integral is convergent. The integral is convergent Then we can talk about the series that we're looking for, right? We want to find out if the series is convergent or not. We found out that the integral is convergent, therefore the series is convergent. And going from 0 to infinity of n e to the minus n squared is convergent. So that's a second example to use the integral test. Integral test is probably I wouldn't say the easiest, but if you try to connect the idea of integrals give you the area under the curve with series which give you the summation of all those rectangle areas, I think it's easier to understand and apply if you can make that connection. It may or may not be the easiest test for series. Where did the -1 come from? So the -1 is this part. So when I plug in 0 into e to the minus x squared, I get -1 here. And that stays after I take the limit. Because when we take the limit, only the first term is affected by t, so that goes to 0. So I still have -1, so that becomes a -1. When I multiply with the -half in front of it. I don't know if you are familiar with this notation, just a side note. When you put 3 dots together, that's like a therefore. Also, whichever. And then a while ago. So that's the integral test. It works well when you have function that's positive, decreasing, continuous, or continuous positive decreasing. If you're not sure if a function is satisfying those 3 conditions, you can always plot them first to double check. Obviously, if you have a function that's increasing, it's not going to help. So that's the integral test. Any questions before we move on?
So it's a finite number, so it's convergent, right?
For the integral, if the improper integral that we're looking for, if at the end, when we take the limit, we end up with a finite value, then the integral is convergent. Therefore, the series is convergent. Now, the next one, I'm going to skip the work that for the deriving it. I'm just going to write down the test directly. It's called P-series test. So if so consider series of the form so sigma, let's see, n equals k to infinity of 1 over n to the p. P is the exponent, where p is just a real number. P is real. So consider some series in this form. If it's not in this form, you cannot apply this test. You might have to do some manipulation in order to use it in this form. So P is the exponent in the denominator. If K is greater than 0, the series n is going from K to infinity, 1 over n to the P is convergent if I probably should write P's, write P's real, K is positive. So let me rewrite this. So that series, this one, if P is greater than 1, then the series n from K to infinity, 1 over n to the P is convergent. So we just look at the value of P, but you always want to make sure that the series in this form, the AN is 1 over n to the P. And 2, if P is less than or equal to 1, then the series 1 over n to the P is divergent. This is easy test, but it's very limited. It's only applicable to this type of series. It's not a very widely used test, but it could be really useful from time to time. I'm not writing down the derivation for this test, but it's in the book if you are interested. So for example, let's just consider the series 1 over n and going from 1 to infinity, right? By just looking, well, we have done this before, right? If you remember that when we saw, like, you know, I don't know, did we do this? I feel like we did it, but I don't remember. I think we've done something like this. You can use the integral test, right? You can do from 1 to infinity, 1 over x dx. And if you remember, actually, you know what, I remember now, we did this integral, improper integral before, right? So if we do this, we found out that this integral is divergent, right? And if you want to use integral test, we can see the series is also divergent. Therefore, the series n equals 1 to infinity, 1 over n is divergent, based on what we have done before. But let's not use the integral test. Let's just use this like a P-series test. Well, first of all, let's look if that series is in the correct form. It is, right? N equals 1. That's the case 1, so that's positive. And then 1 over n is sort of in the form of 1 over n to the P, but with P being 1 here, so P equals 1. It is in the correct form, and the P equals 1. Well, if P equals 1, we look at the second line, it says if P is less than or equal to 1, the series is divergent. Because P equals 1, it's in the divergent part. So therefore, the series is divergent. It's a lot quicker to make the conclusion. So where you only use this test if you have the series is written in the form of 1 over n to a power, with n being the index number. Sorry, now I see what you meant. It's how do you put it? A lot of times that in I guess it's more like in examples that involves like there will be a lot of examples that you cannot calculate the value directly. You would have to kind of like consider using a sequential approach to solve a problem. I don't know if you heard about something called finite difference. That's one method. It's sort of a numerical approach to solve a problem. But before you start solving it, you want to know if you can actually find a solution. So that will depend on whether the sequential approach will give you a convergence or divergence. Trust me, if you want to keep studying math, eventually you will use this. And in a lot of proofs, you want to prove some, I don't know, some theorem in mathematics, or some kind of, well, not prove the theorem, like, yeah, or some kind of statement you want to prove. You might have to use, you might want to show something is convergent or divergent in that process. Yeah, but for now, let's just feel comfortable to apply it to certain examples. So the next example, I'm going to ask you to tell me n going from 4 to infinity of 1 over n to the 7th. Is this convergent or divergent? 1, 2, example 2. Well, that's like a 2 and a 3. How about this one? Series n equals 1 to infinity of 1 over n to the negative 7. And example 4. Series n from 1 to infinity of maybe that's just too easy. How about let's replace this one? I just say n to the 4th power. Some of them you can just see it immediately, right? But, and how about this one? 1 over cube root of n squared. Right? So let's just look at those ones. The second example, this one. We have 1 over n to the 7th. Is this convergent or divergent? It's convergent, right? So we just look at, see if it's in the correct form. It is, right? It's in the form of 1 over n to the p, with n going from k to infinity, and where the p is 7, right? So p equals 7, which is greater than 1. According to the p series test, if it's greater than 1, it's convergent. So therefore, series converges. How about n to the 4? It's divergent. Good. So, well, obviously, you know, we can just look at n to the 4 directly, right? If we just consider 1 to the 4th plus 2 to the 4th plus 3 to the 4th, and we know the sum will go to infinity, right? We know that's a divergent series. But what about, let's try to rewrite it using the p series test. So let's take this and write it in the correct form. We have to have 1 over something, right? So the series we can write as 1 over n to the 4th power, right? That's n to the 4th. So that's the same thing as a series of 1 over n to the negative 4. It's in the correct form, and the p is 4. P is negative 4, which is less than or equal to 1. is in the second category. So therefore, the series is divergent. Okay, good. How about the last one? It diverges. Good. Excellent. So again, we just have to do a little bit algebra to make it in the correct form, right? So I'm going to rewrite the denominator using exponent. So that becomes series 1 over, that's good, but it's n squared, so n squared, cube root, so 2 over 3. And the 2 over 3 is a p, which is less than or equal to 1. Well, it's less than 1, we know that, right? So therefore, it's in the second part of that test. So therefore, the series diverges. So I think this test is the easiest, but again, it probably cannot be used in a lot of cases. It has a very limited use. But if you have some series that in this form, you can immediately use it. All right. Any other questions before we move on? So there's one more test, actually 2 more, but I want to at least go over another one with you. How you go to that form. Some functions you cannot put it into this form. If you can, always try to make sure that the numerator is 1. Or if you have a constant, that's okay. Like if you have 5. So for example, let me give you this one. For example, if we have series 5 over, let's just say 5n squared over n to the 5th power or something like that, and divide by 2, something like this, right? Well, let me finish this and I'll explain a little bit more to your question. So if you have something like this, the 5, we want 1 there. So the 5 doesn't matter. You can always bring it outside, but for now, let's just leave it. The n squared divided by n to the 5th. So that gives you 5 over, if you minus divide by n squared from numerator to denominator, so n to the half, right? And the 5, we can always bring outside of the integral. I mean, not the integral, sorry, the summation, the sigma notation. So we get 5 sigma 1 over n to the 1/2. So that's in the correct form. Don't worry about the 5. You can just focus on the sigma part. Now, in to answer your question, if we just look at the denominator, you get cube root n squared. If you have this radical form, in an algebra class in the past, you probably learned that the cube root just means that you have a 1/3 as an exponent. The square of n is just a square, right? So if you rewrite them by combining 1/3 and a 2, you just multiply them together. That will give you n to the 2/3 in the denominator. Okay, so so in the example here, from this step to that step, so what I did is I divide by n squared. It depends, right? There's a couple of ways to go. You can, how about this? Because we're dividing, let me take a different route. So we are dividing n squared by n to the 5/2. So when we divide, we subtract exponents. We can write as n to the 2 minus 5/2. The 5, I'm just going to put it aside. This 5, don't worry about it. Just leave it. Right? When you divide, you subtract exponents. So that becomes n to the negative 1/2, right? Because that's n to the 4/2 minus 5/2 equals n to the negative half, which, because it's a negative exponent, so you can write as 1 over n to the half. Hopefully that makes more sense. That's one way. The way I did it is I have n squared divided by n to the 5/2. I just divide by n squared from numerator and denominator. And the numerator is 1. The denominator becomes n to the 5/2 minus 2. Becomes half. Any other questions before we move on? All right. The next one seemed to be should bring some familiarity. We have done this before with integrals. It's what we call a comparison test, but it's the direct comparison test. If you understand the comparison test for integrals, this should be just the same, but it's for series. It works the same way. So let me write it down first. So suppose we have series an and the bn, so n going from 1 to infinity, if you like, or k to infinity for the math, and the series n going from k to infinity, but let's just make 1 for simple, to make it simple, of bn. So those are two series, an and bn, with an, bn positive all the time, so greater or equal to 0. So an doesn't matter what n is, an is always positive, bn is always positive, and an less than or equal to bn all the time. So for all n. So if you remember this upside down a means for all. This is n. This is my notation for n. So for all n, an is always less than or equal to bn. So if we consider, I'm going to use different color here. So if we consider this is the sequence of an, and the bn is always higher, but they are always positive. So bn is like this. It doesn't have to be decreasing, right? So bn could be going up and down, up and down. But oops, do it right. But bn has to be, if you pick an n, bn has to be greater than an or equal to. Right, that's a condition. So if we have those, then we can make conclusions. The first one is, if the series of bn, the bigger one, the series of the sequence that's bigger, if you add them up, you get a series. If bn is convergent, then the an, the smaller series, is also convergent. That's the first part. I probably should, no, okay. The second part, if the smaller series an is divergent, then the bigger series bn is also divergent. So this is what this thing is, that if the sum of bigger numbers, so that's Bn, the big numbers, right? So this says if sum of the bigger numbers go into a finite number, then the sum of smaller numbers will also go to a finite number. It makes sense, right? And then the second one says if the sum of smaller numbers goes to infinity, then the sum of bigger numbers also goes to infinity. Kind of like that we compare the two area, right? When we talk about integrals, it's the same concept. So maybe I should write if sum of bigger numbers is finite, then sum of small numbers is finite. And then the second one says if the sum of smaller numbers is infinite, then the sum of bigger numbers is also infinite, right? Think about divergent means sort of like approaching infinity. So example. So let's consider this one. So consider the series n going from 1 to infinity, 10 over 3 to the n plus n. We want to know if this is convergent or divergent. You could try to use the test we did before. You can try to use the integral test. I'm not sure how easy it is to integrate. I'm going to erase this in a second. I don't know how easy it is to integrate 10 over 3x plus x dx. I'm not sure. I think it's a little bit challenging if you try to integrate that. You cannot use the p-series test because you cannot put in the 1 over n to the p form. You can try to use the divergence test, but I think it's going to be inconclusive if you try to use it. So we're going to try to use a comparison test. So here we have 10. Now I'm going to show you a trick that sort of makes things a little bit easier. The 10 we can think about as a constant. I'm just going to bring it outside, just leave it aside. Don't even bother about it. So we're just going to write it as 10 sigma 1 over 3 to the n plus n, and going from 1 to infinity. So for now, we're just going to consider this series, the 10 doesn't matter. And then to do that, to try to figure out if this series is convergent or divergent using the comparison test, if you remember that we can pick functions that's bigger and smaller than this, right? So we can compare them with a given one. So here's a 1 over 3 plus x. Excellent. So a function that's smaller than this is 1 over 3 plus n. That's smaller than 1 over 3 to the. So if you don't see this, let me write down this. 3 is less than equal to 3 to the n. For n is like a 1, 2, 3, 4, right? And that means it's 3. Oh, wait a minute. Let me take it back what I said. This might not be right. So 3 plus n will be less than or equal to 3 to the n plus 1. Oh, sorry, plus n. But then if we add a numerator to both sides, we have to flip the sign. So 1 over 3 plus n is greater or equal to 1 over 3n plus n. So it's actually bigger, sorry for that. So 1 over 3 plus n is bigger than the given one. So we want to know this. So this is bigger. So we can try to determine if this series is convergent or divergent. I'm going to erase this part. So let's consider the series 1/3 plus n for n going from 1 to infinity. Right? This one, if you try to, I'm trying to figure out what's the easiest way to do this. We can try to use the integral test. So we can try to integrate from 1 to infinity of 1/3 plus x dx. And I can tell you directly that this behaves just like 1/x. 1/3 plus x behaves just like 1/x. There's no difference there. The reason it behaves like that is because 1/3 plus n is less than or equal to 1/n. Because when the denominator gets smaller, the value gets bigger. So instead of using 1/3 plus n, you can just use 1/n directly. One of the two will work. So if we use 1/n or 1/3 plus n, and just like integrating 1/x dx, this is divergent. So this series, I'm not showing all the work here, this end up to be divergent. Well, if the bigger series is divergent, we cannot draw a conclusion about the smaller one, right? So if the sum of bigger numbers goes to infinity, we don't know if the sum of smaller numbers will go to infinity or go to a finite number. We cannot conclude. So using this as the an, we cannot conclude. But can we pick a different function that's bigger than the given one or smaller than the given one? Well, what about if we drop the n in the denominator? Because n is positive, right? Oh, so just a quick reminder that if you want to integrate 1/n, 1/x dx, that's just going to be natural log of absolute value of x, if you forgot. You don't just, and that's a special case. So let's pick a different function that's greater. So this one doesn't work. So let's consider that 3 to the n is always going to be less than or equal to 3 to the n plus n, right? Because n is a positive number. So if you add a positive number to itself, it's always going to be bigger. And if we make them into the denominators, not denominators, so we get 1/3 to the n will be greater or equal to 1/3n plus n. So this is the second function that's greater than the function that we want to find if the series is convergent or not. So let's use 1/3 to the n instead. So now we're going to consider the series 1/3 to the n for n from 1 to infinity. And in order to do this, that's a sort of like a quick way to so there's a few ways you can do it. The longer way will be using the integral test. So you can try to find the integral from 1 to infinity, 1/3 to the x dx, and then try to figure out the value from there. Or you can, by just looking at 1/3 to the n, I can write as sigma 1/3 to the n, n equals 1 to infinity. If you remember what I did last time when we talked about geometric series, whenever you have a number, so note sigma a r to the n is geometric series, right? And if you remember that if r, absolute value of r is less than 1, then the series is convergent. If the absolute value of r is greater than 1, the series is divergent. So that's something we talked about last time, probably briefly, that you didn't remember. So here, the 1/3 raised to the power n tells us that 1/3 is just the ratio. You cannot do the p-test because it's not 1/n to a power. So here, so in this case, what's changing is the exponent that's changing, right? The n in the exponent is changing, but the p-test is if the base, so 1/n to the p, so the n is changing in that p-test, p is constant. Correct. If it's n to the cube, you could, but not here. Good point. So here we're just going to, by just looking at it, I know it's a geometric series because of it's like a r to the n. So this is geometric. And with r equals 1/3, which is less than 1, therefore the series is convergent. So when we use 1/3 to the n, we found out that the series is convergent, right? But remember that 1/3 to the n is greater than the one that we want to know. So this tells us that the bigger series is convergent. And to go back to what I had earlier in the green box, this one is, so maybe I should write it down, 10 times the series is less than or equal to 10 times the series of 1/3 to the n, the one that I'm using, kind of all over the places now, but hopefully it still makes sense here. This part we found out is convergent and is greater than the series that we're looking for. Therefore, the smaller series is also convergent. I hope it makes sense there. But let me write down in words. Since the series 1/3 to the n plus n less than or equal to the series 1/3 to the n, and the series 1/3 to the n is convergent, therefore the series that I'm looking for, 1/3 to the n plus n, is also convergent. And obviously we had a 10 earlier, so therefore 10 times this, or 10/3 to the n plus n, is convergent. So that's a comparison test. It's just like we have done with the integrals, right? We integrate back then, but now we just look at series. We compare, two different series. One is a simpler function that's either greater than or less than. And I think a lot of you are still confused. Again, in this comparison test, you just kind of have to pick some function. You might pick one. It doesn't give you any conclusion. Try to pick another one, right? Either going to be smaller or bigger. You might be able to find multiple ones that's bigger. So try them all. And you might find, one or two that's smaller than the function given. Try those. Any other questions about this example? All right. It's really a lot of practice. The more you practice, the better. Just try to pay attention to each example. All right, here's the second example. So we want to know if this series n going from 1 to infinity with n divided by n squared minus cosine square n is convergent or divergent. So can anyone tell me which function is greater than this given function or smaller than? So we want to find functions that we can compare directly with n over n squared minus cosine square n. So maybe we can find functions greater than or functions less than. One over n is greater than this. I think 1 over n is less than this given function. You'll be surprised. It might be useful. Well, let's try it, right? So this function, just like the previous function, right? You get multiple parts in the numerator and the denominator. Well, just one part in the numerator, you get two parts in the denominator. So I'm going to try to manipulate the denominator to make it simple. So what I know is that cosine square n is going to be between 0 and 1. Right? If I add a negative sign, I'm sort of flipping it. So if I just add a negative sign to all of them, so I get 0 greater or equal to negative cosine square n greater or equal to negative 1. And if I add n squared to each one of them, nothing changes. So n squared greater or equal to n squared minus cosine square n greater or equal to n squared minus 1. And then I'm going to take all of those, put into denominator, then I have to flip the sign again. Right? So I got 1 over n squared less or equal to 1 over n squared minus cosine square n less or equal to 1 over n squared minus 1. And then I'm going to continue to multiply each of the numerator by n because n is positive. So when I multiply the numerator by n, nothing changes. So the left side is n over n squared, which is just 1 over n. The right side is n over n squared minus 1. Right? So now we have two functions. One is smaller, one is bigger. Let's look at which one we can use. Well, let's try one of them, right? Let's try with 1 over n. Daniel said it doesn't help. We'll find out, right? So let's begin with try 1 over n. Because it's smaller than the given function, so therefore series 1 over n is going to be less than or equal to series n over n squared minus cosine square n. Let's just focus on this series 1 over n. What do we know about this? Well, series 1 over n, for n going from 1 to infinity, I think we just saw this earlier, right? Because this is the n to the power 1. This is a case that you can use the p-test, the p-series test, because it's a 1 over n to the p form. So p equals 1. If you remember that if it's less than or equal to 1, it's divergent. So this series is divergent. We found out that the one on the left is the smaller series is divergent. So the one that's smaller is already, when you add them up, when you add all the terms up, they're already approaching to infinity. What about the series that's bigger than that, the series of elements that's bigger? So because of the smaller one is divergent, therefore the bigger one is divergent. So let me write it down. Since the series 1 over n less than or equal to the series n over n squared minus cosine square n, and we found out that the smaller series is divergent. Therefore, the big one, n over n squared minus cosine square n, is divergent. So this is like the first part of the comparison test. You probably wonder, can we use the other one? I think if you use the other end, you're going to end up with the same. You end up with the bigger one is divergent. If you choose the other end, you get divergent. But because it's on the higher end, you get a divergent series. You cannot conclude something about the lower series. So even if you try the other function, it will be inconclusive. Why is it? So there's a question says, why is it 1 over n, not 1 over n squared? Oh, so what happened is that, so over here, after I get to 1 over n, I get 1 over n is less or equal to 1 over n squared minus cosine square, right? But the given function, it has an n in the numerator. So I multiply all terms by n. So I get n over n squared. Great, still less than or equal to n over n squared minus cosine square n, less than or equal to n over n squared minus 1. And that's where this 1 over n come from. So that's just n over n squared. Because if we didn't have the n in the numerator, we wouldn't have the function that we want to compare because they're different, right? One that has an n, one doesn't. So that's why we need to take extra step to multiply by n. So we end up with 1 over n instead of 1 over n squared. Okay, so that's a comparison test. There will be more examples that I'm going to let you try on your own, and also I can go over a few more examples next time. I'm going to let you go now. It's almost 7:50, so do the homework, and there'll be a new homework coming up. Just watch out for the notification. All right, I'll take care, everyone. Thank you.